Welcome to this problem-solving session. Today, we'll be diving into LeetCode problem number 1744, titled Can You Eat Your Favorite Candy on Your Favorite Day? We'll explore the problem, evaluate different approaches, and break it down step by step. Let's get started. In this problem, we are working with a candy store that contains several types of candies. These candies are represented in an array called candies count, where each element candies count, I, tells us how many candies of type I are in the store. Alongside this, we are given a list of queries, where each query specifies three values: favorite type, favorite day, and daily cap. The goal is to determine, for each query, whether it is possible to eat at least one candy of the specified favorite type on the given favorite day while following a set of rules. First, you must eat exactly one candy per day. Second, you can only start eating candies of type I after finishing all candies of types 0 to I1. Finally, you can begin eating these candies starting from day 0. The result should be a Boolean array, where each element corresponds to a query and is true if the conditions are satisfied, or false otherwise. The output for this problem is a list of Booleans, where each Boolean indicates whether it is possible to eat the favorite candy on the specified day for a given query. Looking at an example, if candies count is 7, 4, 5, 3, 8, and the queries are 0, 2, 2, 4, 2, 4, 2, 13, 1 billion, the output will be true, false, true. Let's break this down. For the first query, the favorite candy type is 0, the favorite day is 2, and the daily cap is 2. This means you want to eat candy type 0 on day 2. To do this, you must have eaten candies on days 0, 1, and 2, so at least 3 candies in total. Since there are 7 candies of type 0, this is possible, and the result is true. Continuing with the second query, 4, 2, 4, here the favorite candy type is 4, the favorite day is 2, and the daily cap is 4. To eat candy type 4 on day 2, you would need to have eaten all candies of types 0 through 3 first, which requires consuming a total number of candies that exceeds what is possible given the constraints. Therefore, the result for this query is false. For the third query, 2, 13, 1 billion, the favorite candy type is 2, the favorite day is 13, and the daily cap is extremely high at 1 billion. With such a high daily cap, it is definitely possible to eat candy type 2 on day 13, so the result is true. Now consider another example. If candies count is 5, 2, 6, 4, 1, and the queries are 3, 1, 2, 4, 10, 3, 0, 0, 1, the output will be false, true, true. For the first query, 3, 1, 2, you need to eat candy type 3 on day 1, but this requires finishing all candies of types 0, 1, and 2 first. Since there aren't enough days to do this, the result is false. For the second query, 4, 10, 3, eating candy type 4 on day 10 is feasible under the given conditions, so the result is true. Finally, for the third query, 0, 0, 1, eating candy type 0 on day 0 is straightforward since you can start eating immediately, making the result true. This problem also comes with several constraints and edge cases to consider. The candies count array can have up to 100,000 elements, with each value being as large as 100,000. The queries list can also have up to 100,000 queries, and the values for favorite day and daily cap can go up to 1 billion. Edge cases include scenarios where there is only one type of candy, ensuring queries for other indices return false. If favorite day is 0, the solution must check if it's possible to eat a candy of the favorite type immediately. Additionally, large values for daily cap and inputs for candies count and queries must be handled efficiently to avoid performance issues. Finally, the solution must account for cases where favorite day significantly exceeds the total number of candies available. Handling these edge cases is crucial for ensuring correctness and efficiency. To tackle this problem, we first considered a brute force approach. This involves simulating the consumption of candies day by day, starting from the first day, and checking if we can reach the favorite type of candy on the favorite day. While this approach might be conceptually straightforward, it quickly becomes computationally expensive due to the need to repeatedly calculate cumulative candy counts and simulate daily consumption. With n representing the number of candy types and queries the number of queries, this approach has a time complexity of O, queries asterisk n. Given the constraints of the problem, where both n and queries can go up to 100,000, this solution is clearly impractical for large inputs. Instead, we turn to the prefix sum approach, which is both optimized and scalable. By pre-computing cumulative candy counts using a prefix array, where each element represents the total count of candies up to a specific type, we can efficiently determine the availability of candies without redundant calculations. This method allows us to streamline the process by ensuring that we can answer range queries in constant time, making it far more suitable for the problem constraints. The prefix sum approach has a pre-processing time complexity of O(n) to compute the cumulative sums, and once this is done, each query can be answered in constant time, O(1). This results in an overall time complexity of O(n) plus queries, which is highly efficient given the input constraints. Now, while an alternative approach using binary search could be considered, it introduces additional complexity without any significant performance gains. Binary search would involve searching the range of candies consumed within the cumulative candy counts, but since the prefix sum already provides direct access to this information, binary search becomes redundant. Consequently, the chosen strategy for this problem is the prefix sum approach. It strikes the perfect balance between simplicity and efficiency, allowing us to answer each query in constant time after an initial linear pre-processing step. Given the constraints, this method is optimal, as both brute force and binary search fail to provide the same level of efficiency or practicality for large inputs. One key insight that makes the prefix sum approach particularly effective is its ability to facilitate efficient range queries. By pre-computing the cumulative count of candies, we can directly determine how many candies are available before and including the favorite type. This leads to an important realization: the conditions for eating the favorite candy on the favorite day can be distilled into a simple range check. If the range of total candies consumed by the favorite day overlaps with the range of candies from the favorite type, then it is indeed possible to eat the favorite candy on that day. Essentially, the problem boils down to efficiently checking for overlapping ranges, which is precisely what the prefix sum technique excels at. When we compare the three approaches, brute force is simple but infeasible for large inputs, binary search adds unnecessary complexity, and the prefix sum approach offers the best trade-off. While it requires a pre-processing step, this cost is negligible compared to the time saved during query resolution. This makes the prefix sum method the most balanced and efficient solution for the problem, perfectly tailored to handle the constraints provided. To solve this problem, we need to determine if it's possible to eat a specific type of candy, called favorite type, on a specific day, referred to as favorite day. To do this, we'll work with three key inputs. First, the candies count array tells us how many candies are available for each type. Second, favorite type and favorite day specify the type of candy and the target day we're interested in. Third, the daily cap sets the limit on how many candies we can eat in a single day. The solution begins by pre-computing a prefix sum array. This array helps us efficiently calculate the cumulative number of candies available up to any type by storing running totals. For example, the first element is simply the count of the first candy type, while subsequent elements are the sum of all previous counts plus the current one. This allows us to quickly access the total candies for any range, which is essential for the next steps. Next, we calculate the range of feasible days for each candy type. For any type I, we determine the earliest day, or min day, you can start eating that candy. This is calculated by dividing the total candies of all previous types by the daily limit. If it's the first type, the minimum day is 0. Then we calculate the latest possible day to finish that candy, or max day, by subtracting 1 from the cumulative total candies for that type. Once we have these ranges, we check if the favorite day falls within the feasible range for the given favorite type. Specifically, we verify that min day is less than or equal to favorite day, and favorite day is less than or equal to max day. In addition to the range check, we confirm there are enough candies available to even reach this type by verifying that the total candies eaten up to favorite day, based on the daily cap, is greater than or equal to the candies required to start this type. If both conditions hold, the answer is true, otherwise, it's false. The key insight here is the use of the prefix sum array to optimize our calculations. Without it, determining the cumulative candy counts for each query would require looping through the candies count array repeatedly, which is inefficient. By pre-computing the prefix sums, we reduce this to a constant time operation for each query. Additionally, translating the problem into simple inequality checks for min day and max day eliminates the need for simulating the process day by day, further simplifying the algorithm. When handling edge cases, we need to ensure that calculations don't fail if there's only one candy type or if the favorite day is very early. For example, if favorite day is earlier than the min-day, it's immediately clear that eating the favorite type on that day is impossible. These careful considerations ensure that our solution handles all scenarios correctly and efficiently. Analyzing the complexity of this approach, the time complexity is driven by two main components: computing the prefix sums and processing the queries. Computing the prefix sum array takes O(n), where n is the number of candy types. Each query is handled in constant time, O(1), using the prefix sums and range checks. Therefore, with Q queries, the total time complexity is O(n) plus Q. In terms of space, the prefix sum array requires O(n) additional space, and the variables used for range checking are negligible in comparison. To illustrate how this works in practice, let's consider an example. Suppose the input is candies count equals 7, 4, 5, 3, with daily cap equals 4, favorite type equals 2, and favorite day equals 5. We'll walk through the steps to determine if it's possible to eat the favorite candy type on the favorite day. Starting with the given inputs, we first compute the prefix sum array. This gives us prefix equals 7, 11, 16, 19, where each value represents the cumulative total of candies up to that type. For favorite type equals 2, we calculate the minimum day, min-day, as the total candies of the previous types divided by the daily cap. That's prefix 1/4 equals 2. The maximum day, max day, is the total candies for the favorite type minus 1, which is prefix 1 equals 15. Now, we check if favorite day equals 5 lies within the range 15. It does. Finally, we verify that eating up to this day satisfies the candy requirement. Multiplying favorite day by the daily cap gives 5*4 equals 20, which is greater than or equal to prefix 1 equals 11. Since both conditions are satisfied, the result is true, meaning it is possible to eat the favorite candy type on the favorite day. This Python solution solves LeetCode problem number 1744, can you eat your favorite candy on your favorite day, by efficiently determining whether the specified candy can be eaten on the given day under the provided constraints. The problem is approached using prefix sums, which allow us to calculate the cumulative candies available for any type in constant time. Let's break it down step by step. 1. Prefix sum calculation. We start by computing the prefix sums of the candies count array. The prefix sums represent the total number of candies available up to and including a specific type. This helps us quickly calculate the range of candies available for any type. 2. Processing queries. For each query, we extract the favorite type, favorite day, and daily cap. Using this data, we calculate two key ranges. Minimum and maximum candies needed. These are calculated based on the day, one-based indexing, and the maximum candies that can be eaten per day. Minimum and maximum candies available. Using the prefix sums, we determine the range of candies that belong to the specified type. 3. Checking overlap. To determine if the candy can be eaten on the favorite day, we check whether the range of candies needed overlaps with the range of candies available. If they overlap, the answer is true, otherwise, it's false. For output results, we append the result for each query to a list and return the final list of Boolean results. This solution is efficient, with a pre-processing step that computes prefix sums in O(n), and a query processing time of O(1) per query. It handles edge cases, such as when the favorite type is the first type, no prior candies, or when daily constraints are very high or low. The use of prefix sums ensures that the solution is both optimal and scalable for large inputs. Here, we start by importing the necessary packages and defining the solution class. The main method we're implementing is canEat, which takes in two inputs, an array candies count representing the number of candies for each type, and a 2D array queries that holds the favorite type, favorite day, and daily cap for each query. The first step in the method is to compute the prefix sums for candies count. This helps us efficiently determine the cumulative number of candies up to a specific type. We initialize a prefix sums array, where the first element is set to the number of candies of the first type. Then, we iterate through the rest of the candies count array, updating each position in prefix sums as the sum of the previous value and the current candy count. Next, we initialize a Boolean array result to store the answers for each query. For each query, we retrieve the favorite type, favorite day, and daily cap. Using these values, we calculate the minimum and maximum number of candies that could be consumed by the favorite day. The minimum is simply the favorite day plus 1, because days are 0 indexed, and the maximum is the favorite day plus 1 multiplied by the daily cap. Additionally, we determine the range of candies available for the favorite type based on the prefix sums. If the favorite type is 0, the minimum candies available start at 1, otherwise, it starts from the end of the previous type plus 1. The maximum candies available for the type is the value in prefix sums at the current type index. Next, we check if the range of candies that can be eaten overlaps with the range of candies available for the favorite type. Specifically, we verify if the maximum candies possible by the favorite day is greater than or equal to the minimum candies available and if the minimum candies needed is less than or equal to the maximum candies available. If both conditions are true, it means it is possible to eat the favorite candy on the favorite day, so we set the corresponding entry in the result array to true. Otherwise, we set it to false. Finally, after processing all queries, we return the result array, which contains a Boolean value for each query indicating whether the favorite candy can be eaten on the favorite day. This approach ensures that we efficiently check the overlap of ranges for each query using the prefix sums, keeping the solution both clean and performant. To solve this problem, we first need to understand the requirements. We're given an array called candies count where each element represents the number of candies of a specific type. Additionally, we have a list of queries where each query asks if it's possible to eat at least one candy of a given type on a specific day, assuming we eat between 1 and a maximum number of candies per day, defined as daily cap. For instance, in the first example, the input candies count is 7, 4, 5, 3, 8, and the queries are 0, 2, 4, 4, 7, 2, 2, 3, 2. The goal is to return a result for each query, indicating whether the conditions can be satisfied. To solve this, the first step is to pre-compute the prefix sums of the candies array. This gives us the cumulative total of candies available up to each type, which will help us determine the range of candies that can be consumed by a specific day. The prefix sums for the given candies count array, 7, 4, 5, 3, 8, are calculated as 7, 11, 16, 19, 27. Each value in the prefix sums represents the total number of candies available from type 0 up to the corresponding index. For example, prefix underscore sums 2 equals 16 means there are 16 candies available in total for types 0, 1, and 2. Next, we process each query to determine if the conditions are met. In query 1, for type 0 on day 2 with a daily cap of 4, the minimum candies needed are 3, and the maximum possible are 12. The range of candies available for type 0 is 1, 7, based on the prefix sums. Since the range, 3, 12, overlaps with 1, 7, the answer is true. For query 2, type 4 on day 7 with a daily cap of 2, the range needed is 8, 16, but the range for type 4 is 20, 27, so there's no overlap, and the answer is false. Finally, for query 3, type 2 on day 3 with a daily cap of 2, the needed range is 4, 8, and the available range for type 2 is 12, 16, resulting in another overlap and a true answer. For query 3, we confirm that the range of candies available for type 2 is 12, 16, from the prefix sums, and the range of candies needed is 4, 8. Since these two ranges overlap, the result is true. Putting this all together, the output for the first example is true, false, true. Now, let's look at the second example to further solidify our understanding. Here, the input candies count is 5, 2, 6, 4, 1, and the queries are 3, 2, 4, 4, 10, 3, 0, 2, 2. The first step, as before, is to calculate the prefix sums, which for this input are 5, 7, 13, 17, 18. This gives us the cumulative totals of candies up to each type. With the prefix sums prepared, we can start analyzing the queries, checking for overlaps between the range of candies needed by the favorite day and daily cap, and the range of candies available for the favorite type. For the first query in example 2, type 3 on day 2 with a daily cap of 4, the minimum candies needed are 3, and the maximum possible are 12. The range of candies available for type 3 is 14, 17, and there's no overlap with 3, 12, so the result is false. For query 2, type 4 on day 10 with a daily cap of 3, the range needed is 11, 33, but the candies available for type 4 are just 18, 18, meaning there's no overlap, and the result is false. Finally, for query 3, type 0 on day 2 with a daily cap of 2, the range needed is 3, 6, and the available range for type 0 is 1, 5. Since these ranges overlap, the result is true. The final output for this example is true, false, true. By following these steps systematically, calculating prefix sums, determining ranges of candies needed and available, and checking for overlaps, we can efficiently solve the problem for any input. The time complexity of our solution is O, n plus m, where n is the length of the candies count array, and m is the number of queries. Let's break this down step by step. First, we compute the prefix sums for the candies count array. This involves iterating through the array once and performing a constant time addition for each element, which gives us a time complexity of O, n. Next, we process the m queries. For each query, we extract the values of favorite type, favorite day, and daily cap. Using these, we calculate the range of candies needed by the favorite day and compare it with the range of candies available for the favorite type. These calculations involve constant time arithmetic operations, lookups in the prefix underscore sums array, and comparisons. Since each query involves a fixed amount of work, processing all m queries takes O, m, time. Together, the prefix sum computation and query processing result in an overall time complexity of O, n plus m. To summarize the time complexity, prefix sum computation takes O, n, query processing takes O, m, and the total time complexity is O, n plus m. Now, let's discuss space complexity. The space complexity of our solution is also O, n plus m. This comes from two main components. First, we store the prefix sums of the candies count array. The prefix underscore sums array has a size equal to n, the length of candies count, so it requires O, n, space. Second, we store the results of the queries in a result array. This array has a size equal to m, the number of queries, so it uses O, m, space. Combining these, the overall space complexity is O, n plus m. In total, the solution uses O, n, space for the prefix sums and O, m, space for the result array, giving us an overall space complexity of O, n plus m. Now, let's compare this optimized approach to a naive brute force solution. A brute force method would simulate the candy eating process day by day for each query. This would involve iterating through the candies of all types up to the favorite day for each query. If favorite day is very large, say up to 10 to the power of 9, the time complexity of this approach would be O, m asterisk favorite day, which is completely infeasible for large inputs. By contrast, our optimized solution pre-computes the prefix sums, allowing us to determine candy ranges in constant time for each query. This reduces the time complexity to O, n plus m, making the solution much more efficient and scalable. The time complexity of our solution remains O, n plus m in all cases. For the best case, even with minimal input sizes or trivial queries, the solution still computes the prefix sums and processes each query, so the time complexity does not change. For the average case, typical inputs involve processing all queries in constant time per query, resulting in O, n plus m. In the worst case, with maximum input sizes, the solution still runs in O, n plus m. To mathematically prove this, note that prefix sum computation involves n additions, which is O, n. Each query involves constant time operations, leading to m asterisk O, 1 equals O, m. Adding these terms gives O, n, plus O, m, or simply O, n plus m. This demonstrates that the solution is optimal and scales efficiently even for very large inputs. One of the most common mistakes when solving this problem is forgetting to handle edge cases properly. For example, you might overlook scenarios where the number of candies starts at 0 or where someone consumes exactly the maximum number of candies allowed on a given day. These off-by-one errors can be tricky, so it's important to carefully manage inclusive and exclusive boundaries in your logic. Another mistake is hard-coding values, like assuming a fixed number of days or candies in your solution. This makes your code less flexible and vulnerable to unexpected test cases, so always aim for parameterized solutions instead of relying on fixed values. Inefficient looping is another issue to watch out for. If you repeatedly compute cumulative sums or iterate over the same portion of the input, you may unintentionally increase time complexity to O, n squared, or worse. Pre-computing cumulative sums or using optimized techniques like sliding windows can help avoid this. Finally, overlooking input constraints can lead to serious problems, especially with large inputs. For example, if the maximum number of candies is 10 to the power of 4, using inappropriate data types in languages like C++ or Java could cause overflow errors. Always validate your assumptions about input sizes and handle them carefully in your implementation. Another frequent challenge is misinterpreting the problem statement. For instance, some people assume they must reach their favorite day or type of candy exactly, when the problem might only require this to be feasible within certain bounds. Taking the time to read the problem thoroughly and testing your solution against various edge cases can help you avoid these pitfalls. From an interview perspective, it's important to recognize that this type of problem often relies on prefix sums or cumulative computations. Identifying this early can guide you toward an optimized solution. If you're dealing with repeated range queries, pre-computing cumulative sums can reduce query time from O(n) to O(1), which is a significant improvement. These problems are often designed to test your ability to handle constraints efficiently, so it's important to demonstrate your thought process when optimizing for large inputs. Additionally, good communication is key. When explaining your solution, highlight how you handle edge cases, such as minimal or maximal input sizes, as this shows thoroughness and attention to detail. This problem is closely related to several others on LeetCode that involve similar techniques. For example, LeetCode 238, product of array except self, is a great way to practice cumulative computations, as it requires you to calculate products without directly iterating over the same elements. LeetCode 303, range sum query immutable, is a classic prefix sum problem and is particularly helpful for understanding how to optimize range-based queries. Another useful problem is LeetCode 560, subarray sum equals k, which focuses on identifying subarrays with specific sums, a concept that's highly relevant to range-based decision-making. Finally, LeetCode 1011, capacity to ship packages within D-days, deals with efficient allocation within constraints, which is conceptually similar to balancing candy consumption over a range of days. Practicing these problems can deepen your understanding of cumulative calculations and optimization strategies, which are critical for solving this type of challenge effectively. There are a few different approaches you can take when tackling this problem. The simplest is brute force, where you simulate each day and check the conditions iteratively. This method is straightforward and can be helpful for small test cases or validating your logic, but it's inefficient for larger inputs due to its O(n)², or worse time complexity. A more efficient approach is to use prefix sums. By pre-computing cumulative sums, you can enable O(1) range queries, reducing the overall complexity to O(n). This is particularly useful when dealing with frequent queries. Another alternative is binary search, which can be applied if you're trying to find a specific day or type within given constraints. Combining binary search with cumulative sums allows for efficient range checking and is particularly effective when the inputs are sorted or exhibit monotonic properties. Each of these methods has trade-offs. Brute force is easy to implement but not scalable, while prefix sums require additional space for the cumulative array but significantly improve efficiency. Binary search offers high performance but adds complexity to the implementation. Choosing the right approach depends on the problem's constraints and the size of the input, so it's important to weigh these factors carefully when deciding on your strategy. Great job! To summarize, this problem highlights the importance of prefix sums for efficient range queries. It also emphasizes the need to handle edge cases carefully. Thanks for watching, and don't forget to like and subscribe for more content like this. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!